Hello, welcome back. Remember last time that we were talking, we realized that we could transfer some mathematical information that we had gotten when we were studying slopes and curves back in our math classes and transfer that slope formula to look at how displacement or position and velocity are related with respect to time, and also how acceleration and velocity are related with respect to time. So velocity, we realize, is the slope on the position versus time graph because it is displacement over time. And acceleration is the slope on the velocity versus time graph because it is the change in the velocity divided by the change in time. So I'm taking just the top formula, velocity is equal to displacement over time, or change in position over time, and looking at graphing position versus time. Notice that we have quadrant 1, quadrant 2, quadrant 3, quadrant 4 for this graph. But quadrant 2 and quadrant 3, if an object had any location in these regions, it would be corresponding to a negative time, right? Time is negative along this portion of the line, and time is positive along this portion. So these two regions, 2 and 3, will never have graphical information for an object's motion. An object can't move backward in time. And of course, the same is going to be true on the velocity versus time graph and the acceleration versus time graph. Anything to do with the time, you cannot plot an object's information for negative time. So we're only going to have region 1 and region 4 information for an object's motion. So here is the formula that we have looked at now in a couple of videos. If I just isolate delta x, notice I'm taking the exact same formula, but I'm just isolating delta x. That amounts to multiplying by delta t on both sides of the equation. So I have the change in position for an object is equal to its velocity times the time over which the position changed. So I want to now look at an object that is moving in some fashion and see how I can infer information from its position versus time graph to draw its velocity versus time graph. So let's say that an object is starting at the origin, and let's say that's the big I in Albuquerque. And let's say that east is the positive x direction. So traveling towards the mountains, positive x direction. And our object, being a car on the interstate, is going to travel to the east, starting at time t equals 0 at the big I, and with cruise control on. So that amounts to a constant speed as well. So it's a constant direction, constant speed. So we're traveling in the positive x direction at a constant velocity. And so that graph for the car's motion traveling in the same direction at a constant speed is going to look like a straight line. So the object starts here at time t equals 0 at the big I, and then moves uniformly away from the big I, headed in the positive direction, which we said was east for the purposes of this discussion. Okay? So here's what our curve looks like. And remember that we learned in the last video that the slope of this line is the velocity. And you can just see that. I mean, the slope is the change in the position for any 2 points you pick divided by the corresponding change in time. Well, that's rise over run, and that is the definition of the slope. So velocity is the slope, and you can see that the velocity is the same, or the slope is the same at all points. I can find the slope at any one point, and it's going to be the same as the slope at any other point. Slope doesn't change, velocity doesn't change. So what would that look like on the velocity versus time graph? What kind of a curve would show velocity as a constant over time? Well, that's just a horizontal line, right? So we've got a velocity, let's say that this is the velocity, and it's just going to be constant over the time interval. So velocity doesn't change. So in other words, the velocity at this time is the same as the velocity at this time, is the same as the velocity at this time, is the same as the velocity at this time. So the velocity doesn't change. Now let's look at this rearranging of the formula and see do I get any information by looking at the velocity versus time graph to infer information about the position versus time graph? In other words, what if I didn't have this graph? What if I was just looking at this graph? I knew that the velocity was a constant with respect to time, and so I could draw the velocity versus time graph. And now I want to see, can I infer position versus time graph from the velocity versus time graph? And the answer is yes. So look at the form here. This is velocity times change in time. So here's the velocity, right, that we're traveling at, v, or that the car is traveling at. And this quantity right here corresponds to the change in time. So there's the velocity that we traveled times the change in time. So if I take this velocity and I multiply it by this change in time, what significance or what information do I get? Well, I get the area under the curve. So the displacement is equal to the area under the curve on the velocity versus time graph. This is really important information for us. As we're going to see, we're going to have 4 relationships that we're going to want to keep track of so that we can find graphical information for one quantity by knowing graphical information from another. So now we know that velocity is the slope on the position versus time graph. We also know that displacement is equal to the area under curve on velocity versus time graph. Okay, and this is always going to be true. I mean, here it's a very simple shape. It's a rectangle, but it does not matter what the shape is. If we can find the area under that curve, that will correspond to the object's displacement. Okay? Notice that this is positive area because it is above the time axis. If instead we were traveling to the west in the car, and that would correspond to a negative x, then we would be traveling with some constant negative velocity, and that would be just a line that's the mirror image down here below the time axis. That would correspond to negative area. And so therefore our displacement would be negative, which would make sense because if we're traveling in the negative direction, our final position is going to be more negative than our initial position. So if we take the displacement final position over the initial position, then minus the initial position, then we're going to get some negative quantity for the displacement. Okay? So it can be positive or it could be negative, as we've talked about in earlier videos. Okay, so we have these 2 graphical connections. Now let's look at drawing the acceleration versus time graph. So here is the object moving at a constant rate away from the origin. We see it has a constant velocity. So our velocity versus time graph is just a straight line. What would our acceleration versus time graph look like? So here is acceleration versus time. And acceleration is change in velocity over change in time. So what's happening to our velocity? What is the change in the velocity? Well, I could pick any 2 points. I'm going to have the same value for the velocity here as I have for here, or here as I have for here, or here as I have from here. No matter what 2 points I pick, I'm going to be subtracting the same velocity from itself. And so I'm going to get an acceleration of 0 for this object's motion, which is the car moving with uniform velocity away from the origin. And so an acceleration of 0 for all time is just going to correspond to a graph that looks like this. So not a whole lot of information we're going to be able to relate off of this graph back to velocity, but we will in the next video. We're going to pick a more complicated motion for the object and see how you can infer information about the acceleration versus, or the velocity versus time graph from the acceleration versus time graph. So let's save that for